So here we have another example of a given differential equation, and we want to find a general solution and a particular solution containing the ordered pair 2, 4. So to start, I get all the y stuff on the left and the x stuff on the right. Oh, by the way, if there's a constant involved as well, keep that on the right with the x, because we want y to be isolated for our final function, meaning that we want as little stuff with it as possible. Okay, so moving things around, I get 1 over y squared times dy equals x times dx, okay, divided by y squared multiplied by dx. And then we take the antiderivative of both sides. This is y to the negative second, so the antiderivative is negative 1 y to the negative first, or negative 1 over y. And we don't need a plus c. Okay, then over here, antiderivative is 1/2 x squared. We do need a c on this side. So to get our general solution, we need to solve for y, so we're going to need to do a little bit of algebra. I'm going to start by dividing everything by -1, which shortcut here is just going to do this. A constant divided by -1 is still a constant, so I do not yet need to, I don't need to put minus c right there, okay? And then we can do this one of two ways. We can think of it as multiplying by y and then dividing by this entire thing, or we could just take the reciprocal of both sides of the equation. Either way, we get the same algebraic result. We get y equals 1 over negative 1/2 x squared plus c. Now I don't want to leave it like this, so I'm going to multiply by -2 over -2, which is -2 over x squared plus c. Okay, so y equals -2 over x squared plus c is my general solution. Okay, for part B, I want to plug 2, 4 into this function and get a particular solution. So let's label this. This is part A. This is part B. So 4 goes in for y equals -2 over 2 squared is 4 plus c. So let's go ahead and divide by 2. So multiplying over here, we get 8 plus 2c equals -1. Now, you might notice that I did not leave this in terms of c. As soon as I've plugged an ordered pair in for x and y, then that c becomes locked. Okay, it has a value now, and so I can't, anything that happens to c has to be represented. Think about what we know about the equation for a line. Y equals mx plus b in slope-intercept form. M can be anything, b can be anything, but as soon as we're talking about a specific line and we start plugging points in for one value or the other, then M and B get have a specific constant numeric value. Okay, all right, so let's subtract 8, so we get, and then divide by 2, so we get -9/2 for c. Okay, now that's not our solution, that's just the constant, which is really arbitrary in the context of the problem. Our particular solution is y equals -2 over x squared minus 9/2, which, let's get rid of that complex fraction again, we get y equals -4 over 2x squared minus 9. Okay, I do want to show you one other way that we could get to this. Remember I said in the last video that if we're looking for a particular solution, once we have, which would be right back here, once we have a function, okay, once we've taken our antiderivative, we can actually plug the ordered pair in here and solve for c. Again, once you plug in the ordered pair though, the c value is locked. So to get to our particular solution, okay, I'm going to say, or using this, I'm going to plug 2 and 4 in, so we have 1 over, well, I already divided by -1. It doesn't really matter when you do that. Okay, so 1 over 4 equals -1/2 times 2 squared, which is 4, plus c. And so we get 1/4 equals -2 plus c. So here c is 1/4 plus 2, which is 9/4. Okay, now notice I don't have the same c value here. Remember I said that c is arbitrary? It doesn't really matter what c is. And it's not that we're saying that there are two possible functions, but the way that this equation is written and the way that this equation is written have had something done to C. Remember here I multiplied by -2 and I left it as C. Well, -2 times 9/4 is going to be -9/2. And really that's not even something you need to worry about, because if we have that C equals 9/4, just make sure you plug it into the form that you used of the equation that you used to solve for C. And when we rearrange, we'll get the same thing. So let me show you what I mean. We get 1 over y equals -1/2 x squared plus 9/4, okay? And then and then take the reciprocal of both sides, so y equals 1 over -1/2 x squared plus 9/4. I'm going to multiply by -4 over -4 to get those complex fractions out of there and get rid of that negative. And I get y equals -4 over, there's a 2 left, 2x squared here, 4's cancel out, -9. Okay, so as you can see, we do have the same function, but we went about solving it different ways. Okay, next example is a motion application. So if you've taken physics, you've probably already seen the formula that comes from this, this process of solving the differential equation, but I want you to understand where that comes from and be able to derive the formula for the vertical position of, you know, whatever object. I don't know what the formula is called. Okay, either way, we want to get to that formula. All right, acceleration due to gravity changes depending what planet you are on, also depending what units we're in. Since we're in feet per second here, we are going to give our acceleration in feet per second. And acceleration due to gravity on Earth is a constant, and it's about -32 feet per second squared. Okay, if we are in meters, acceleration due to gravity is about -9.8 or -9.81 meters per second squared. So just use the same units that are in the problem. Okay, and so this is our, let's put some equal signs in here. This is our acceleration due to gravity, and again, this is on Earth, and it is a constant. Okay, so I wrote it as a function, a of t, okay, but for any time t, acceleration due to gravity is always -32 feet per second squared, okay? And, sorry, I forgot to leave room for this, so you can skip down to the bottom if you need to, if you printed this, okay? So we are trying to write a function that represents the height of a ball that is thrown upward with this 40 feet per second. That's a velocity, that's a rate of change of distance over time. So this is actually our initial velocity, or I'm going to write that as v sub 0 or v of 0. Either notation is fine. And then from the top of a 100-foot building. So this right here is our initial height, which we could write as h sub 0 or h of 0. Either notation is okay. All right? So it's height at time 0 or in function notation. So, working backwards, we start with our acceleration function. We know that acceleration is -32, okay, feet per second squared. And then we know that acceleration is the derivative of velocity. So to get from acceleration, okay, we can take the antiderivative of this with respect to t. Let me rewrite this. So antiderivative of a of t dt is going to be the antiderivative of -32 dt, okay? And the antiderivative of acceleration with respect to time is going to be velocity. And the antiderivative of -32 with respect to t is not -32x, it's -32t. And then remember, we need a plus c, okay? For our particular situation, this is where we use initial velocity, because we know that the velocity at time 0 is equal to 40, so we can say v of 0 is 40, which is -32 times 0 plus c, so that means c must be 40, okay? So I'm going to come up here. Our v of t function, our particular solution then, is that v of t is negative 32t plus 40. Okay? And then we know that velocity is the derivative of position, meaning that position involves the antiderivative of velocity. So now I'm going to take the antiderivative of v of t with respect to t and the antiderivative of negative 32t plus 40 with respect to t, and I get position, or because we're dealing with vertical position or height, I'm going to use h. So h of t is equal to antiderivative here with the power rule, negative 16t squared plus 40t plus some constant. And again, we have an initial height. We know that the height at time 0 is 100 feet. So we could say the height at time 0 is 100, which is equal to negative 16 times 0 squared plus 40 times 0. You probably don't need to write this part, but it doesn't hurt to have it in the notes. Plus c, and so we know that c then is 100. So our function for the height of the ball is h of t equals negative 16t squared plus 40t plus 100. Cheating there, okay? And here is our function, okay? One more example with differential equations. This one is not solving a differential equation. This one is showing that this function is a solution. If you see a question about asking if a function is a solution, or which of these functions is a solution to the differential equation, or which of, or given a function, it's a solution to which differential equation, something like that. If you're given the function and a differential equation, do not actually try and solve the differential equation, okay? There are a lot of differential equations that we don't even know how to solve. Whether or not I could solve this right now doesn't really matter because I already know my function. I just want to know, is this a solution to this? In other words, does this satisfy this equation? Okay, so let's look at this equation in terms of this function. This says that dy over dx, or in other words, the derivative with respect to x, plus x over y is equal to 0. So what is dy over dx? Well, using the chain rule here, our derivative is 1/2 times 1 minus x squared to the negative 1/2 times negative 2x. Okay, again, chain rule there. And so I want to take this and add it to x over y and see if that's equal to 0. Okay, so plugging into here, we get negative, I'm going to condense this a little bit, negative 2x over root 1 minus x squared plus x over, and then what is y equal to? Y is root 1 minus x squared, okay, equals 0. Is that a true statement? Oh, I'm sorry. No, it is not, because I forgot to cancel the 2's. Okay. Take 2, doing what I like to call the right way. We have negative x over root 1 minus x squared plus x over 1 minus x squared. Yes, it is a true statement. That is equal to 0. So we have showed that this is a solution to this differential equation.